Okay. Yeah. So this week, I mean, for today's lecture, we are going to um, talk about linear regression model. Okay. So we can think of it as one of the most basic type of supervised machine learning models. And actually, it is a so classical topic, and it's almost for sure will be covered in statistical classes. Okay. And it's a very basic type of computational tool to study the relationships between two or several more variables in um, basically um, a very broad range of types of data observed from the real world. Okay, and I think it's a good entry point for our course to start with, because um, the contents that I put in the slides will be slightly different from those offered by stats course, and we will focus more on the implementation. And as an introduction to this next level of slightly more complex supervised learning models. Okay, and let's look at the next slide. So as a preparation part, we will first look at briefly how we will present data um, as the very first step of a typical machine learning project or machine learning pipeline. Okay, and then we will define the linear regression problem by introducing um, several terms, several mathematical terms. Okay, and the third part will be the part for solving the linear regression model, or to another language, another word, we can say, how do we train a linear regression model? Okay, so there will be basically two methods that we will cover. The first type, normal equation method, is the traditional um, way that is usually used in statistical analysis. Okay, and they have very fast implementations in current statistical analysis software packages. Okay, but more importantly, we will go through the second type of method called gradient descent method. Okay, because gradient descent will be the basis for almost all the supervised learning machine learning models in the future that we will talk about already. Okay, so this is the mental model that we introduced in the first lecture. So the model, whenever we talk about machine learning model, we can use a set of parameters represented by a series of Greek letters. In this case, we use theta, right? We can have more than one parameter, okay? And usually we have more than one parameters, like theta 1, theta 2, theta n. That is the typical way that we notate the parameters, okay? And with parameters in this red box, we will use them to fit the training data. And the training data comes into smaller chunks if the total data set is too big, okay? And after the parameters have been trained, then we will apply those thetas to the new data, okay? And the new data is never observed before in the training set, okay? So this is just a brief review of the mental model here. So the first question that we need to figure out is, how do we represent the data as a common practice? Okay, we will introduce the idea of features, the concept of features. Okay, so features are the numbers or the numerical methods that we use to represent the data, so that the data can be loaded and can be used to train the parameters, to train the model's parameters. All right. The example that we use here is from a classification problem. Okay, so we wanted to, given a fish, we want to tell it is a salmon or sea bass. Okay, it's a binary classification, a typical binary classification problem. So how do we solve the problem if we want to learn it ourselves? Okay, like we're given a bag of fish and we can do whatever we want to do to it as long as they give us information, right? So you can, for example, measure the length of each fish, to weigh each fish, to smell it, touch it, right? So anyway, we have a bag of training data. Okay, so what we need to do as a first step is to extract features from this bag of fish. A very simple example is to measure the length of it, right? Using a ruler of it, we can measure the length for each fish in the bag. Okay, so after we have done that, well, it's a lot of work, right? After that is done, then we can plot all the length metrics that we have got, okay? And we will plot it into a histogram. So a histogram is a plot that shows the distributions of your target quantity. And in our case, it is a distribution of the length of fish. Okay. So in this case, assume that we already know what each fish is, right? For each fish, or we're already given a label that this is a salmon or sea bass, and that we have measured its length. And after we have plotted the histograms of the two fish in two colors, we see that the distribution tell us something about the difference between the two kinds, right? The majority of the length for salmon seems to cluster more on the left side of the chart, while the median value or the majority of the length for the sea bass is more on the right. Okay, so it's kind of a solution that we can come up with at this point, because if we use a vertical line here, represented by this, indicated by this dash line, right? We can use that boundary as a empirical decision boundary. So whatever fish that we encounter in the future, if it's lower than 11 inch, right? We can probably claim that, or make a guess that it's more likely to be a salmon, right? Because on the left of this 11-inch boundary, the majority will be the salmon, while on the right, the majority will be the sea bass. Okay, so length seems to be a feature that works. Well, we know that it is working, right? But it's not perfectly working. Okay. Yeah, so if we can do this, we can sort of make this work, but it is for sure to make some mistakes. Okay, yeah, might not work for other unobserved data points. Okay, so what we can do to improve this simple model is to add another feature, right? If we can use more features, that means we can describe the data from more angles, from more perspectives, right? So this time, let's add the color, the lightness of the color, for example. Say we have a way to measure the lightness, and we do the same thing for the lightness, for the lightness data we have collected. And it seems a better better separation of salmon and the sea bass if we use only lightness as a feature. As you can see, right? If we use the boundary in the middle, then the distributions of the data on either side are more pure, right? There are more salmon on the left and more sea bass on the right. It is not as mixed as the previous feature, right? So it seems lightness is a better model, okay? So given these two features, we can combine them, right, all together as a way to uh, develop a more sophisticated model, okay? So in this case, when we plot the data using two features in two dimensions, the x-axis is the lightness and the y-axis is the length. So now we can have a sort of a contour plots or a two-dimensional distribution of all the data points. And the decision boundaries is more salient in this case, right? Because now we have a feature of two-dimensional, right? It's actually two sizes. We have the size equal to, we have a one lightness as the first dimension and the length as the second dimension. Okay, so now our feature becomes a vector. Okay, so the term vector is something we used a lot to describe, especially for long features, for larger data sets that have a lot of features. Okay, right. So any data points that we have can be described by these two-dimensional vectors. Okay. All right. So it seems that adding features will, improve the performance or improve the way that we can classify the data points, right? But actually, we need to be careful about adding new features because some features may not be good informative ones, like the number of eyes, right? And weight may be already closely related to the linear to the length, right? So it may not be that informative to add weight when we already have the lens feature. And color may be useful, smell may be useful, but we need a way to quantify those features, right? Okay, and next on this slide, we'd like to slightly touch or introduce an issue that is interesting and also always important when we describe machine learning models. Okay. Right, we have these three different types of decision boundaries, and we have the last type of decision boundaries. Okay, so all those different decision boundaries are developed by different types of models, and especially when we are comparing the last three types, because they both utilize two features, right? The only difference is that the decision boundary here is a straight line, while this one is a curved line, right? And it looks that the curved line makes better predictions, right? Because more black ones are correctly predicted and more red data points are also more accurately predicted, okay? But this case, the last case here, when the decision boundary is a more sophisticated, a super complex decision, super complex nonlinear curves, it is a problem that we will more systematically introduce, which is called overfitting. Okay, so in the last case, all the data points fall onto the correct side, right? But it may not be, it is not likely to be a good model to new data points, right? Because the boundary doesn't capture the general patterns. It is more of a description of the idiosyncrasies of the current training set, but not generalize very well to new data. Okay. All right. So we don't need to like fully understand what the implications of the overfitting is. We will have a more thorough introduction to it, but it's a good visualization to see how different models may result in different performance. All right. Okay, so as a recap, when we want to train a supervised learning models for simple classification tasks, the first step will be choosing features, right? And then we collect data and we represent data with feature vectors. And then we choose a model, and the different model results in different boundaries, okay? And training and make predictions, okay? So that's pretty much the procedures that we will take for a supervised learning task. So it's really the mapping between the features vectors to the labels that we wish to achieve when we train a model. Okay, and the training data need to contain labels. And in this case, in the example we introduced, it's a binary label of either 1 or 0, 1 for salmon, 0 for salmon, 1 for sea bass, for example. Okay. So given any test example, we can compute a feature vector X, and then use that new feature vector X to predict the label. Okay. Yeah. So that's a introductory example that I would like to use here to introduce our first linear regression model. And on the next slide, there is a slide distinguish supervised versus unsupervised. I think I'm going to skip it for now, and we'll leave it to the future lecture when we first talk about unsupervised learning. Okay. All right. Now let's look at the linear regression problem. How do we mathematically define such a problem? Okay. All right. We will look at a different task. Now, the task that we looked here is to predict the housing price. We know the housing price depends on various types of factors, right? But so we can define the label first, right? The label, which is the price of the house, is actually a continuous number. Okay, it's we will give a notation of y in this case. Okay, and it's a supervised learning problem because we will first collect a lot of data that maps the house to its price in a one-on-one style. Okay, so when we collect data, there will be a lot of features that will be closely related to the housing price. For example, the size of a house, the number of bedrooms, where it is located, when the year of the building, right? So, whoops. Yeah, so assume that we have collected sufficient amount of data, and then let's try to first visualize our data, right? And when we only use one feature for simplification, we only use the size to predict the house, the price, right? And this will be the how the data visualizes, right? The size and the corresponding price, size, corresponding price, and so on. Okay. Right, that's our very first step. The next, let's give some formal mathematical notations. Okay, let's use x to indicate the feature. And in this case, the feature is just one number. It is not a vector yet. Okay, just for simple demonstration here. And our label is the y. Okay, and note that we here give the superscript i's to each x and y to indicate that is the i's data points or i's data instance among our data sets. Okay, and then we will define our models. Okay, our linear regression model. We will use a single parameter theta 1 as our parameter, and we use the multiplication or the product of theta 1 times x to predict the target label, which is y. Okay, so this is a simple way to utilize the features and the parameters. Okay, there will be one parameter involved here. Okay, but in actually on next page we will see that the total number of parameters is actually not just the theta 1. We will introduce another parameter, which is theta 0. Okay, because we will soon find that only use theta 1, our parameter, our model will be a limited one because there's no way to take into consideration of the intercept. Okay, so anyway, let's replace what we used to have in this red box with theta 0 and theta 1. That will be the collection of parameters in our model. Okay, that is basically the construction of a simple linear model, simple linear regression model. We will need an intercept parameter theta 0 because that will make the model much more flexible. Okay, so let's look at the problem more officially defined. What our goal is to learn a linear function, okay, that maps from x to y. The way we write this linear function is to put theta here as the subscript f theta of x. It's a simple linear form, which is theta 0 plus theta 1 times x. Okay, and if we plot this function with x and y axis, that is basically how it looks like. Okay, right? If we extend the line, the linear line here, we will see that it will hit the y-axis with the value of theta 0, and the slope of it is actually defined by the theta 1. Right? If we measure the slope of it, right, it will be defined by the theta 1. Okay, that's how it looks like in this two-dimensional space. Oops. So we can interpret the model's parameters with intercepts and intercepts and the slope. Yeah. But here our task is to find the theta and the theta 0 and theta 1s that can fit with our data with the best fitness score. Okay. Okay, let's go to the next slide. All right. So you can see here, let's see how different combinations of theta 0 and theta 1 would result in different models. If the theta 1 is 0, it means the slope is 0. Okay, that is a strange case because the price doesn't change with the housing or with the house size, right? Which is not likely in real world. Okay, and the second case is y equals 0 plus a positive theta 1. And a zero intercept means that the price of a house will go will decrease to 0 if we have a 0 size house. So that is also not realistic. Okay. A more likely case is that both theta 0 and theta 1 have positive values, right? With the intercept of 100 and the slope will be 0.11, for example. Okay. All these numbers are just examples. Okay. All right. So the problem is that how do we find the best theta 0 and theta 1 given a data set looks like this, given our training data look like this? Okay. So we can arbitrarily draw a linear line, right, in this red color, and it seems fits the data to some sort of degrees, but seems not a good fit because on the two ends, the data points deviate from the lines, right? And among these three cases, it seems that the blue one is the best one because the visual distance from the blue line is the closest to the black data points, right? So we wish to choose parameters so the linear function is close to y for all the training data points. Okay, so that is a guideline we can actually use to train the linear regression model. Okay, so let's build on top of this guideline. Right, we need to define what we mean by close. We need to measure the closeness, right? All right, so now let's mark the predicted value of the linear function, right, with this y hat notation. Okay, so the xi is from the real data. It is the size of a house, right? And we will substitute xi into the linear function, which is theta 0 plus theta 1 times xi, which will give us the predicted value in y hats, right? And what we can do is that we can plot the line and the predicted values y hats, right? And on this plot, we plot the predicted values together with the real values, the actual values, right? So you can see that there are some deviations. The actual price for the first house is y1, but the predicted value would be y hat 1 according to the model, right? So there will be a distance between the actual value and the predicted values, right? So that is how the first step of computing the distance between the predicted value and the real value. All right. We go to the next step. Right. Let's highlight the distances between those values. Okay. And our objective here is to minimize the distances. Okay. Because if a model produces too much distance between the prediction and the actual value, then it's not good model, right? We want a model to make as close prediction as possible, right? So our learning objective becomes more clear. We want to minimize the differences between the predict values and the ground truths, right? That is, we want to minimize a summation of squares, okay? A summation of y1 minus y hat 1 square plus y2 minus y hat 2, y2 hat, right? And so on until the last data points. Okay. And this is the so-called cost function. Okay. It is a function that measures the correctness of the model when we predict y with x, right? And if we write it more formally with thetas and yi and xi, it'll be a summation of a bunch of squares, right? And there is a normalization term here, 1 over 2n. We don't need to know why it's over here, because later we will see the functions of it. Okay, so when we substitute the formulas for computing y hats into this form, into the term in the middle, we will get the term to the right, right? It'll be a summation of y minus y f theta of x to the square. Okay, and this type of cost function is also called mean square error, right? And the meaning is straightforward. All right. So, well, one thing we need to keep in mind is that the function j here, it is a function with respect to theta and theta 1. So thetas are the unknowns, while all the x and y's, they are known because they are from the training data. Okay, so what we need to find are those theta 0 and theta 1 that best that minimize this cost function. Okay, so now that the problem has been defined, let's step into the next part. How do we solve the linear regression problem? Okay, and actually in this simple linear regression case, by simple I mean there's only one feature, right? We only have one feature, and there's only two parameters, theta 0 and theta 1. So we can easily expand the cost function by replacing this linear function with its actual form here. And we expand the square term, and we will get a bunch of products, right? So it looks like a very typical quadratic functions, right? The red part and the blue part, they are all quadratic functions with respect to theta 0 and theta 1. And when we ignore all those x and y's, and because they are constants, because they are from the data, right? We can basically write our cost function into this form. Especially, we pay attention to the coefficients before the quadratic term, right? The coefficients before x theta 1 and theta 1 square and theta 0 square, they are all positive numbers, right? These a and c, they are all positive numbers, which means it's a quadratic function with positive coefficients before the quadratic term. It is a function that we can find a minimal point, right? We can always plot the shape of the quadratic function like this, right? When we have a positive coefficient a here, right? In this particular example, what we plot here is y equals x squared minus x minus 2. Okay, we can always find the points where this cost function, where this function is minimized, right? Because our goal is to minimize the cost function. This is good news for us. All we need to do is to find the point where we reaches the minimal the minimal point. Okay, and according to the property of the function, quadratic function, the function will reach its minimal value whenever its derivative hits 0, right? And the derivative of a function is pretty easy to compute. Okay, so we can apply this method to the cost function. Okay, and we need to compute the derivatives of this j of theta of 0 and x theta 1, right? Because we have two unknown variables, theta 0 and theta 1, we can do the derivatives respectively, and we need to find the point where both of these derivatives reaches zero. Okay, so when both derivatives are zero, the cost function will be reaches its minimum points. Okay, and the trick is that when we compute the derivatives with respect to theta 0, the other theta 1 can be treated as a constant, right? So it can apply the rules of the principles of calculated derivatives to make them 0. So let's work out these derivatives. Okay, I think it's a fun practice, and it's a refreshment of our calculus knowledge of basic quadratic functions. Okay, so when we take derivatives with respect to theta 0, okay, you see that we will remove this exponential 2, right? So this 2 will be eliminated with this one in this denominator, right? And the exponential term is gone. And the coefficient before theta 0 is also moved to outside the summation function. Okay, so the derivative of j with respect to theta looks like this sum of these linear forms. And we need to make it 0 because we want to find the minimal points. Right? And the derivatives of theta 1, similarly, we will remove the exponential term, right? And move out the negative symbol, but also the coefficient of theta 1, which is xi. So the xi also remains here. Yeah, remind that xi is a constant. Okay, so we can make these two derivative equations to 0 equal to 0, right? And it's actually can be further simplified, right, into more simple terms, because you can notice that the summation of y divided by m is actually the average values of y. And same is the summation of xi, which is the value of, which is the average, which is just a simplified case. Okay. And for the derivative of with respect to theta 1 is slightly more complex. So we need to rewrite the summation of the products, right? And also the summation of the xi square here. And the middle term here is the xi. Okay. And we have two linear equations and two unknown variables. Okay, so that is good. We can solve these two linear equations, right? And all those coefficients, they can be easily computed, right? Because they are all from data, all from our existing x and y's. Okay. This definitely can be solved. Okay. So I'm gonna skip the part how we solve this. Okay. We know it can be solved, and the solution is summarized on the next page, which looks like, okay, my PowerPoint freezes. I'm not sure what happens. Let me click on it again. Okay, that is how the solution looks like. Okay, and it has a name for this solution. It's called normal equation. Okay, so yeah, looks complex, but actually all those terms have clear statistical meanings, right? The y bar is the mean value, x bar is the mean value for x, And for theta 1, in the numerator, it is the covariance between x and y, and the denominator is uh, um, the variance of the x. Okay. So with these solutions, we can easily solve the parameters theta 0 and theta 1. Okay, which means our model is obtained. We have done with the training of the model. Okay, it's just through this calculation using the normal equation solutions. Okay, so now we can use the theta 0 and theta 1 to make predictions. Okay, and we can also interpret the meanings of theta 0 and theta 1s. Like the slope theta 1, it measures how much the price will change when size changes for 1 unit, and so on. Okay, and it's easy to be applied to a new data point, x new, right? We just use theta 0 plus theta 1 times x new. Okay, clean and nice, right? So now let's proceed on to a slightly more complex examples. We know that in real case problems, it's usually more helpful when we have multiple features, right? Let's include the year of the house and the location of the house as other features, okay? And note that here we added a first column, which is the intercept, because we want the intercept to be also trained. And just for convenience, we will give a dummy feature, which are all ones, okay? So that we can directly apply theta 0 to this column. Okay. Yeah, that's our associated parameters from theta 0 to theta 3. Okay. And the linear function that we use will be theta 0 plus theta 1 times x1 plus theta 2 times x2 plus theta 3 times x3. So now the model looks like slightly more complex. We have n plus 1 parameters. Okay. Assume that we can have multiple. We're looking at n-dimensional features. Okay, so this is called multiple linear regression. We have the same goal, which is to map x to y, right? And our y looks like this. And our predictive value. Okay, I see a question. I'm reading the direct message. Let me know your question is, what your question is. Okay, so it's a question about why theta 0 is correlated to the first column. Okay, so if we go back to the case for, let me reshare the slides again. Let me go back to the simple linear regression case. So in a simple linear regression, when we have only one feature, we will use theta 0 and theta 1 as a model. Okay, so our equation looks like theta 0 plus theta 1 times x. And actually, there is a implicit number, which is 1 over here, right? So the actual function is like y equals theta 0 times 1 plus theta 1 times x, right? So it's like as if there is another column in our feature which has a constant 1, right? Although it's not directly reflected into our original data sets, right? But we can imagine that actually each feature comes with another additional column, right? That's something we can imagine here. So it also applies to the multiple linear regression parts. So what's the difference? Another question I see here, what's the difference between x and xi? Yeah, I represents the i's data point in the data. Okay, so you would like to figure out the difference between the actual y value and the predict y value. Okay, so right, let's look at this same slide here. So the actual value y1 here, for example, it is this value, 399.5. Okay, and the predicted value y hat, right, y hat 1, for example, it will be the results of theta 0 plus theta 1 times x superscript 1. Okay, and x superscript 1 is this value, right? 856. Okay, so the value of y hat depends on what theta 0 and theta 1 we use. If we, for example, we have theta 0 equals 0 and theta 1 equals 1, for example, then the calculation tells us that y hat 1 will be 0 plus 1 times 856. So the y hat 1 will be $856,000. It seems like a bad prediction because it's very far away from the actual price. Okay, so when we change thetas, the y hat will change, right? But our goal here is that we want to find the best theta 0 and theta 1 so that the difference between the y hats and the y are minimized. Okay. All right. These are good questions. Okay, let me the actual, just a follow-up to the previous question, the actual y will not be 856. Let me see. The actual y is determined. The actual y is what's in the table. So yeah, 300 something. Sorry, can't see the prediction. You can't see the question because I'm not sharing my screen correctly. Let me go to where we stopped the last time, where we have our multiple linear regression. Oh, you can't see the question. I'm making annotations on my share screen, but I wonder why it's okay. Yeah, sorry about the confusion. My laptop is not working. Not working correctly. Okay. Yeah, let's continue with the multiple linear regression. All right. Okay. So it's just an expansion or extension of the simple linear regression case. We have longer linear functions, and the predicted value would be the same as theta 0 plus theta 1 times x, blah, 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 until theta n times xn, right? And the cost function will also be defined in the same style, which is the summation of the square of distances, okay? Within the square term, we have the actual value minus the y hats, okay? I see Rush, okay? I see a direct message, yes, I would say it's a yes, okay? yi minus y hats, okay? The only difference is that the equation is longer. All right. So because we have longer equations, we would like to use some simplified way to represent the data. And the matrix is a good choice. Okay. We can now represent our data with a matrix with m rows and n plus 1 columns. Okay, that is how we represent the x. And our y will also be a n row and 1 column vector. Okay, so let's further represent our model's parameter with a theta vector, which is n plus 1. Okay, because we have parameters from theta 0 to theta n. So that's n plus 1 rows of parameters. Okay, and which is written like this. So we can make predictions by multiply the matrix X with the vector theta. And if we write it down, it'll be like this. Okay. We need a refreshment of how do we compute the matrix multiplications. The first row of the X will be taken to compute the dot product between theta 0 to theta n. Okay, that'll result in the first y hats. And for dot product, it'll be the production of theta 0 with the 1 plus the production, the product between theta 1 and x1 and so on. Okay, so that's how we write it in matrix multiplications. Okay. And if we check the dimensions, they need to follow the principles of matrix production. We have the number of columns here match the number of rows with theta. All right, let's look at the next page. Yeah, so next, the cost function can also be rewritten. It's written as the y minus y hat transposed, because y is a vector in n by 1 dimensions, and so is the y hats. And the results of transposing y minus y hats will be a 1 by n vector. Okay, so the production, the multiplication here is also a way to compute a dot product between the vector with itself. Okay, so the j will be written like this. If we substitute the y hats into the function here, right? Because we know y hats is the product, is the product of x times theta, and y hat is also replaced here. And by the principles of linear algebra, we can remove the transpose outside into the inner terms. So that'll be y transpose and x times theta transposed. And we expand all the terms just like a multinomial term production. And finally, we can basically combine the same term, right? We can combine the same term here, which is there's a two coefficients here, okay? So finally, the term would look like this. And when we put all those parameters, all those transposes to each of those matrices and the vectors, okay? We move these transpose into each item of these products, okay? So eventually it looks like this. We can treat the matrix as if it is just a regular scalar variable. Okay. And then what next? We can do the same thing as the normal equation solution for simple linear regression. Remember, we want to compute the derivatives of the cost function with respect to both theta 0 and theta 1, right? And the difference here is that we have more than two thetas. Our theta has n dimensional, okay? And this is also a quadratic function with respect to matrices, right? With respect to long vectors, okay? But in nature, it is still a quadratic function. Okay, so let's do this quickly on next slides. We can compute the derivatives of the cost function with respect to theta. And our knowledge in linear algebra and calculus can help us accomplish this. For example, the term here, theta transpose times x transpose times y, when we take the derivative of it with respect to theta, it's just like a linear term, okay? And when this term, when we take a derivative of it, it's just like a quadratic term. We can apply the similar rules to this calculation by removing, by keeping only those constant parameters, constant coefficient here, right? These constants is reserved here, and there will be a additional constant 2 here because it's a quadratic term, and then we remove the exponentials. Okay, and we will make it 0 because that's the condition of how to find the minimal points of the cost function. Okay, it is analogy. It is very similar to the scalar case. Okay. Okay, so we can do some further transformation of these equations. Okay, I'll use another color. We can move this term to the right, right? So and remove and eliminate all the 2's. So it'll become x transpose times x times theta equals x transpose times y. Okay, and we can further remove the x transpose times x to the right by multiply it with the inverse of the matrix. Okay, the inverse of a matrix have a interesting property. That's the summation, the product of an inverse with the matrix itself will result in an identical, like a unit matrix in which the diagonal lines are all ones. Okay, so anyway, we can have this solution in a very compact form. The theta will be the x matrix transposed times x itself, and we compute the inverse of it times x transpose again and times y. Okay, these x and y's are just the data. They are the data itself. Okay, So the theta can be solved with a very compact solution, which is in a much nicer form than the previous non-matrix representations. Okay, it's the so-called normal equation solution for multiple linear regressions. And you can refer to this link for more detailed introductions to this topic. And I think most of the statistical books will cover more details than this. But I think for our course, this will be enough practice so far. And in our first assignments that I'm going to release this afternoon, we will have a part to implement this normal equation solution for solving the multiple linear regression problems. Okay, so several tips for computing the derivatives of the cost function with respect to vectors. We can remember that the derivative of something is always the same dimension of the variable. Okay, when we have theta is two-dimensional, then the derivative of theta is also two-dimensional. So that should be always a match. Okay, because the derivative of a theta, the derivative with respect to theta is a measurement, is a computation like this. We compute the derivative of the cost function with the first component of theta, second component until the last component. So this is always the same dimension as theta itself. Right? That's a fact that we can use to examine whether our calculation is correct or not. And dimensions is always something we can check to make sure that our calculation is correct. For example, the dimension for theta in our case is n+1/1. For y, it's n/1. For x, it's n/n+1. So, and also the cost function is just a one number. So the dimension of it is 1/1. Given this knowledge, we can quickly check that the multiplication between x transpose and x, it's n+1/n multiplied with n/n+1. So the n will be eliminated, and the result will be n+1/n+1. And the inverse of it doesn't change the dimension. So when we multiply the results of the inversion with x transpose, the n+1 will also be eliminated, right? And when we multiply it with a n/1 vector, the m can also be eliminated. So the result will be a n+1/1, right? Which is exactly the same on the left side. Okay, so that is typically how we can use dimensions to check whether our calculations are correct or not. All right, so that's pretty much for linear regression and the normal equation solutions. Okay, and with this part introduced, I think it's already enough for you to start working on the next assignments of linear regressions. But I would like to use some time that we left, maybe 5 more minutes, on introducing the more critical parts, gradient descent method. It's okay, we don't finish it today. We can leave it to our next Tuesday's lecture. But I think it's better we get a start with it. The quiz questions will not be tested about these equations. Okay, I think the quiz questions will be easier to do. Yeah. Okay. So the main goal of using, well, the purpose of using the gradient descent method is that we do have some issues with the normal equation method. It's fast to compute when we have fewer features, but it will be very problematic when we have a large data set that have a lot of more numbers of features, right? So our matrix is n plus one dimensional, right? This quantity, the x transpose times x is n plus one dimension, n plus one by n plus one. So when n is large, it's very difficult to compute the inverse of this large matrix. Okay, so that is the problem of the normal equation method. So let's look at the gradient descent. First of all, the term gradient is just another name for partial derivative. Okay, a derivative is defined on the function on single variables, but we have multiple variables. We can use the term gradients. Okay, so it's basically a vector. A gradient is a vector of partial derivatives. Okay, when the function is defined against a vector, x can have multiple dimensions. So the gradient of the function is the partial derivatives of the x with respect to the first dimension, with respect to the second dimension, and the last dimension, and so on. Of course, we can replace the x with whatever other notations we have. For example, the thetas, right? So that's basically the same formula. Okay, and next, and gradients measure the sensitivity of the function. It basically measures how much the output will change if the input changes only a little bit. Okay, so in the 1D dimensional, when we have x plus y plotted against x, then the gradients will be the delta of y divided by delta of x when x reaches a very extremely small value. Okay. Slides stops working. Yeah. So that's for a more the second plot is for a nonlinear function, right? But we do the same thing. We increase x a little bit by change the function values a little bit. And also applies to a multiple dimensional case, right? When we have two inputs, x and y to the function, we can calculate the gradients along each dimension respectively. Okay. Let me go to the next slide. Okay, so I will finish this slide and then let's end the class today. So the gradient descent algorithm basically utilize the fact that the gradient is a vector, right? And this vector always points in the direction of the fastest increase of function. So it means that on any point of a function, and when we compute the gradients at that point, if we work along the direction of gradients, we are actually working along a direction that the function will increase fastest. So in that sense, if we go opposite against the gradients, then we are actually working along the direction that the function will decrease fastest way. Okay, so it is a fact that we'll utilize to find the minimal point of a function. Animations stopped here. Yeah. So whenever we want to find the minimal point of a cost function, and our input can be a vector, we can start like with some random values. Start with a theta 0. And we don't know whether this is the minimum or not. And very likely it will not be the minimum. And we will choose a direction to change that theta 0 a little bit to theta superscript 1, so that our cost function decreases a little bit. But in order to do it efficiently, we want to choose a direction along which the cost function will decrease for the fastest. Okay, and we will repeat this step until the cost function no longer decreases. Okay, and the final cost function value will be the minimum values that we claim to find. That is basically what the gradient descent algorithm is about. Yeah. So let's continue our conversation on this gradient descent algorithm on next Tuesday. And after linear regression is done, and we will start our next topic for logistic regression. All right. If you have questions, you can let me know by now or send me emails later. Okay. I'm going to reboot my system. It's the PowerPoint slides running too slow. I'm not sure why this is the case. All right.
Hi, Professor, is the quiz due tonight or tomorrow night?
The quiz is due tomorrow night.
Okay. All right. Thank you.
Mm-hmm.
Have a good one.
Yeah, no problem. Thank you. Okay. Let's see a message. Yes, sure. Yeah, I already posted my PowerPoint slides on Canvas. I'm going to quickly update it because I noticed it's a wrong version. So for group projects, I will provide several options for you to choose from. I will publish the available projects to choose early in early February. Yeah, I'm finalizing some of them. Yeah, hopefully that answers your question. It's hard to describe, but it'll be a lot of supervised learning based projects. Yeah, one of them will be like predicting given a data sets, and you'll be asked to implement different types of models to predict one of the target variables. Yeah. And there will be also other different types of computer vision related tasks and the natural language processing related tasks. Yeah, that'll be nice. Yeah. So anyway, we are online for this week, and hopefully I can see you soon. We will meet you soon after February 7th. All right. Thanks for coming. I will end the meeting now. Thank